So I'm going to talk about some applications of some of the things that have already been introduced, weak temperature gradient theory and interactions between convection and moisture, to bring up the concept of a moisture mode. And I'm going to apply this to intraseasonal variability. I was thinking about doing both intraseasonal variability and easterly waves, monsoon depressions, but I felt that that would be a little bit too much. And so I think I'm just going to concentrate on the MJO and BSISO here. So this is the part of the workshop where you probably are going to start seeing the same plots over and over again that have already been introduced. So I think repetition is good, however. So just as a reminder, the tropics are characterized by weak temperature gradients, and I showed this during my lecture on Monday. And I did a scale analysis that shows you that there's characteristics of the tropics that we can derive, given weak temperature gradients that kind of fall out of the various equations. And one of them was this condition here, that's the thermodynamic energy balance in the tropics, where on synoptic timescales, adiabatic cooling is balanced by apparent heating. And apparent heating here includes not only condensational heating, but also radiative processes, and also subgrid scale eddy flux convergences. And again, S is dry static energy, where that's given by C sub P plus GZ, and Q1 is the apparent heat source. So as I justified on Monday, on time and space scales in the tropics, characteristic of things like the MJO, this balance holds reasonably well. And it also suggests that adjustment under gravity is not explicitly important for the dynamics of disturbances on these timescales. All right, so let's talk a little bit about moisture again and water vapor. One of the projects that I'm helping to lead actually looks at expressions like this. And so this is a famous paper by Brotherton et al. 2004. And what they did is they went to various ocean basins and looked at how precipitation rate on daily mean timescales depends on a quantity called saturation fraction. So saturation fraction is basically what happens if you add up all of the precipitable water in the atmosphere that exists at a given time and divide it by the total maximum precipitable water that could exist given Clausius-Clapeyron. It's just like a column relative humidity. And you can see here that at low column relative humidities, daily mean precipitation is low, but as you get towards relative humidities of 0.7 and higher, then it very rapidly picks up. So you could derive a functional exponential form of the relationship between precipitation and precipitable water, relative humidity in the column, that you could actually use for parameterizations of simple models like moisture modes, which I'll show later. Using very simple relationships like this have their deficiencies, and I'll bring up some of those deficiencies as well. It turns out if you're looking at things like the MJO, that one of the groups is going to be looking at, the MJO might take a trajectory like this. In early phases of the MJO, it proceeds like above this curve, and then later phases of the MJO, it proceeds below this curve, so that on average, the behavior looks like this, but there's a lot of subtleties depending on what phase of the large-scale disturbance you might be looking at. All right, so another interesting thing is in the Australian monsoon region. I actually had a lot of questions after Michaela's talk about how the Australian monsoon region differs from other monsoon regions, and we could talk about that later. But anyways, this is a nice analysis by McBride and Frank in 1999, and they had a sounding array over ocean, the Gulf of Carpentaria, in the Australian monsoon region. And they looked at various quantities relative to rainfall. So there were actually two rainfall peaks here during this year, one in January and one in February, that were associated with MJO events going by. And one really interesting thing that you can see here is that during periods of high rainfall, there's actually an anti-correlation with CAPE. And so if you were to have a climate model which was just dependent on CAPE for its convection parameterization, it's very, very unlikely that you would be able to properly simulate this. Instead, what rainfall was related to was the tropospheric moisture, mainly the free tropospheric moisture content. All right, so this is one of my favorite papers, and we've seen these plots already during this. And so this is an analysis by Holloway and Nealon. And what they did was they binned rainfall into different precipitation bins, high precipitation rates and low precipitation rates. And the precipitation rates are shown here on the y-axis. It goes from 10 millimeters per hour on the top to near zero on the bottom. And then what they did is they looked at what the specific humidity of the column and the relative humidity of the column looked like for these different precipitation rates. And you can see here for the highest precipitation rates, the column is moist versus the low precipitation rates where you see low humidity in the column. And one interesting thing that's also been noted already is that the biggest specific humidity and relative humidity variations are actually above the boundary layer in the lower to middle free troposphere. Certainly there are boundary layer humidity variations which can't be neglected, but the biggest mode of variability in humidity is in the lower to middle free troposphere. So this again provides evidence of the strong connection between humidity and precipitation in the tropics. So some of the reasons for this have been noted already. One of the big reasons for this functional dependence is the role of entrainment. This is a paper by Zhao and Austin, 2009, where they ran a high resolution cloud model with I think they initiated it with a bubble near the surface or something like that. And this shows the evolution of the cloud. And this is a relatively shallow cloud. It only goes up to 1.5 kilometers or so. What they did is they looked at the evolution of this cloud, and it went through a layer of tracers. So that's this black area here. And you can see a clear ingestion of tracers into the cloud, into this sort of toroidal circulation associated with the cloud cap. And the nature of this entrainment is episodic, and so it's not constant with time, and that's been the basis of convection parameterizations like buoyancy sorting schemes like Raymond and Blythe and Emmanuel schemes. But clearly, if you ingest environmental air, particularly if it's really dry, that's going to affect the buoyancy of convective clouds. And Holloway and Nealon looked at this, and so what they did is they had generated a very simple cloud model. One was initiating the cloud with environmental conditions and assuming no entrainment. And you could see here that there is some scatter in, so each of the colors on here are different environmental humidity. So high environmental humidity is in maroon here, and low environmental humidity is in blue. So you can see that with no entrainment, there is some scatter that is created by boundary layer humidity differences. But in all cases, as the cloud goes up, the cloud is still buoyant, except for maybe this one lowest case where it looks more neutral. So you would get convection in all of these cases without entrainment. But if you assume a realistic entrainment profile, and it's called deep inflow B, that's not important. Basically what it means is that entrainment of air into the cloud is highest near the surface and lower aloft. If you have an idealized entrainment profile like this, you can see that ingestion of environmental air now has a big effect on virtual temperature, such that now only really the highest precipitable water content atmospheres have positive virtual temperature deficits, surpluses as you get to the upper troposphere. And then these other clouds here in blues and greens probably wouldn't survive. This paper also looked at different assumptions about entrainment. It's a really interesting paper. I highly recommend it. But anyways, this shows one of the ways that dry atmospheres can affect convection. There's other ways as well. Dry atmospheres also affect downdrafts and cold pools and things like that that can feed back onto convection, but this is one of the major ways. All right, so there's a tight coupling in general between precipitation and tropospheric water vapor. And this coherence between precipitation and water vapor becomes particularly large at certain time and space scales in the tropics. So I showed this last time. This is an OLR spectrum showing the symmetric component of OLR that you can use to diagnose the strength of convective activity at different wave numbers and frequencies. And convectively coupled Kelvin waves are here. Equatorial Rossby waves are here. The MJO shows up down here, as we've seen before. If you were to look at monsoon depressions, they'd be up in this region. They don't show up very well in a symmetric spectrum. They might show up well in other types of spectra. But anyways, this is what it looks like in OLR space. And this plot here shows the coherence, how closely rainfall and precipitable water are coupled together as a function of wave number and frequency. And you see that the MJO is actually relatively unique in that it has a coherence squared of 0.6 or greater between rainfall and precipitation. So indicates that water vapor plays a very strong role in the dynamics of the MJO potentially. And then another paper that I'm a part of, and I actually, interestingly, don't remember it too much, but it is very nice, looked at the amount of precipitation variability that moisture variability explains for various convectively coupled modes in the tropics. And this paper showed that basically variations in column water vapor can explain all of the MJO related variability in precipitation for the MJO. And then it goes down for other equatorial waves. So by the time you get down to Kelvin waves, African easterly waves, and mixed Rossby gravity waves, it's only 1/2 of the precipitation variance explained. So anyways, just to show again that the MJO tends to be relatively unique in its importance of moisture to its dynamics. All right, so what we know so far is that the tropics are characterized by weak temperature gradients. Precipitation is closely tied to free tropospheric moisture, particularly on intraseasonal timescales. And so this suggests the existence of modes of tropical variability in the atmosphere that are explained by processes regulating the tropical moisture field. And if you regulate the moisture field, you regulate convection. And these types of modes are called, have been termed moisture modes. It was originally termed moisture modes by Dave Raymond back in some early papers in the late 90s and early 2000s. But maybe me and Adam Sobel and Angela Adamus and Dan Kim helped to more popularize this term after those initial studies. This has not started, so I'm going to start this. I have an extra 10 minutes or 15 minutes. All right, so we've seen what the MJO is, but I'll go through some characteristics again. So it's the leading mode of intraseasonal variability in the tropics, starts here over the Indian Ocean and then propagates towards the east with time, and at least the convective signal dies out here over the Central Pacific or South Pacific Convergence Zone, down in this region. This is a boreal winter version of the MJO. So I'll show you what boreal summer looks like in a little bit. But you could see various characteristics of convection at least in this plot. The MJO is also coupled to a large-scale circulation. This is the correlation between precipitation and U-850 with an Indian Ocean reference point. So, at 90 east, I think. So just like the previous plot, lag in days is on this axis. You can see the eastward propagation of precipitation with time. And that kind of dies out here, right near the date line, at least in boreal winter. And then you see a wind anomaly associated with it. So generally at low levels to the east of MJO convection, you have easterly wind anomalies, and to the west, you have westerly wind anomalies. And at least in the warm pool region, propagation is on the order of 5 to 10 meters per second. Once convective coupling lapses here near the date line, you can see that this large-scale circulation propagates much more rapidly off to the east. Something more akin to a dry Kelvin wave-like propagation speed. So there's a break here in propagation speed of the large-scale circulation, whether you're in the warm pool or outside of the warm pool. And this is a nice figure from Angel showing, what MJO structure looks like, in 3D. So let's imagine, this is, this red dot here is over the Indian Ocean. So as I talked about before, at low levels, you have east winds to the east, west winds to the west. And at upper levels, it's just the opposite. So you have this, very simple, the first order baroclinic structure with, air flowing out at upper levels. So a lot of interesting characteristics of the MJO, which I won't be able to talk about in full, but one thing you notice, there has been a lot of discussion of different, cloud modes, trimodal cloud populations and things like that. You tend to see this, like Bellon talked about with the MJO, where you tend to get, starting from shallow clouds, they build up to congestus, to deep convection, and then stratiform, tends to trail. So you see that sort of structure with the MJO. So that's one thing that's really, really interesting. Many simple moisture mode models, as I'll talk about later, don't account for these structural changes as the MJO progresses, which you might argue is one limitation. There's also some other interesting things you see on here. You see these Rossby gyres at low levels. Look like these Modon, type structures that were discussed yesterday. You see surface convergence here. This is something that's not captured explicitly by moisture mode theory. There's actually a relatively weak equatorial pressure trough that extends off to the east of the MJO. And in the boundary layer, this drives convergence towards it. So that might actually help to support some of these, cloud populations and building of cloud populations off to the east. Another thing I won't talk about is the fact that there are sea surface temperature anomalies associated with the MJO. So this region tends to be warm. And so, like Divya talked about yesterday, there's, this Linson and Negum model that, if you have sea surface temperature gradients, you could force surface convergence, and that tends to act on MJO timescales as well. I wrote a paper with Simon DeZerka talking about that for the, MJO. The other thing I'd point out here is that you see these Rossby gyres behind here. If you looked at the total anomalous wind field, you would see gyres of the opposite direction off to the east. So there's a lot of interesting nuance here that we could talk about. There are temperature anomalies actually associated with the MJO. So there's warm and cool. I would argue that these are second order compared to the general weak temperature gradient conditions, but you have to have temperature anomalies like this to get a large scale flow like the Gilles model, for example. All right, so that's boreal winter. So boreal summer looks a little bit different. So this is from Sperber and Anomaly, 2008, where they did a composite life cycle of boreal summer variability, at least in this region. And you can see here that, convection starts over the Indian Ocean again, but in addition to it going eastward, it also goes northward. And so it produces these northward propagating rain bands, through southern Asia here. that are associated with active and break periods and onset, of the monsoon, and that's an active area of research I know for some people in this room. I wanted to zoom out a little bit. Whoops, that's not the right one. I wanted to zoom out a little bit. There was a question about synchronized I think you brought it up, synchronized active and break periods of monsoons across the globe. And this might help to answer this question. This is a boreal summer zoom out of what the interseasonal oscillation looks like. And you can see over the Indian Ocean, just like that previous animation I showed, indication of northward propagation. But one interesting thing during boreal summer is that there is a connection through the waveguide here to the east coast of the not the United States. I guess if Donald Trump had his way, this would be the United States. East coast of Americas. And you could actually see here that this initiates a region of convection in the North American monsoon region, just to the south of Mexico and Central America. And then there's an opposite phase here. What's interesting about this is that the phase relationship between precipitation and that over India is actually opposite. So it's more like a seesaw. So you might see out of phase breaks between the two regions. And this actually, this large circulation here that reaches the coast actually has consequences that affects tropical cyclones, not only in the East Pacific, but also the Atlantic. The Andes and mountains along the coast here are actually also very important at blocking the eastward extent of this large-scale circulation. There is intraseasonal variability over Africa and the Atlantic associated with the BSISO, but you see it's quite a bit weaker than it is in other regions. All right, so let's look at some ways that people have used to diagnose the MJO. So the vertically integrated moist static energy budget is used a lot to understand MJO dynamics and also understand MJO dynamics in the context of moisture. And I'll explain why that is a little bit here. So Kiran Mai and some of my earlier work looked at this. So again, moist static energy is H equals C sub PG plus GG plus LQ. You could use other variations of this like frozen moist static energy if you wanted to conserve energy more exactly. I'm just going to use moist static energy because it's pretty good to first order for a lot of things we want to do. And then the vertically integrated moist static energy budget, you have a tendency term, you have a horizontal advection term, vertical advection term, vertically integrated radiative heating, and then latent heat flux plus sensible heat flux at the surface. So those are the components, and we've seen various variations of this before. And the brackets here represent a vertical integral. All right, so there it is again. So recall, under weak temperature gradient theory, horizontal temperature variations are small, and also temperature fluctuations are relatively weak. And also we have this dominant thermodynamic scaling that we derived from the thermodynamic energy balance. So we could also do a little bit of partitioning of this equation as well. For example, there's an omega vertical velocity here. I'm going to break it up into two parts. One, omega r, which is part of the vertical velocity that's driven by radiation, and another part directly, and another part that's driven by condensational processes, omega sub c. So I'm going to do a partitioning there. All right, so what I'm going to do is I'm going to rewrite this term here. So omega dHdP, I'm rewriting the vertical velocity in terms of a radiative part and another part. I'm going to multiply that through. So we have omega c dHdP here. And then we have this omega r term multiplied by dHdP, but I'm going to separate that further into a part that multiplies dry static energy and a part that multiplies latent heat. So break it into 3 different terms here. The other thing I want to remind you of is that you have this dominant thermodynamic energy balance here. So if we're thinking about a radiative heating, that's going to be balanced by omega R dSTP. All right, so one thing you'll notice here is that there's an omega R up here on the right-hand side of this equation. And then there's going to be an omega R dSTP here. That's going to be on the left-hand side of an equation based on the expansion of this term. So those are going to cancel because of this dominant thermodynamic energy balance. And so given the assumptions of horizontal temperature variations being small, the temperature tendency being negligible to first order, and also this dominant thermodynamic energy balance, the vertically integrated moist static energy budget under WTG conditions basically becomes a moisture equation. So we have moisture tendency plus horizontal advection of water vapor plus omega C, which is the part of vertical velocity driven by condensational processes, plus this radiative moistening term, I'll call it, is equal to latent heat flux plus sensible heat flux. Technically, I probably should have brought this radiative term over to the right-hand side here to serve as a source, but I'll show that later. So basically, wanted to make the point here that one reason why people look at moist static energy budgets under WTG is that it's basically a moisture equation. Yeah. It does not guarantee it. I mean, you could have well, if you had negative anomalies, obviously. I'll show you some applications of that in a little bit. No, it doesn't guarantee it. And in fact, if you just look at the shortwave part, it's a damping. Yeah. All right, so basically, we have a moisture equation, which is equivalent to the, approximately equivalent to the moist static energy budget, good approximation under WTG. So at least as far as the MJO goes, I mean, this equation, the moist static energy budget had been applied many previous times, going back to Yadai, Nealon and Held, papers like that. But I think this is the first paper that applied it to look at the MJO. And so basically, what we did here, what I did here is I was sitting at a location in the Western Pacific watching the MJO pass over. Day 0 here is when precipitation, I think I was actually looking at when wind peaked, westerly winds peaked with the MJO, but you can see when precipitation peaks here. And all of the moist static energy budget terms, I used M to represent moist static energy in this paper rather than H, but it's basically H. All of the moist static energy anomaly terms are here. So we got one of the first looks at what helps to maintain the MJO and what helps to propagate the MJO off towards the east with this budget. So for example, we were able to see that horizontal advection led MJO moisture and precipitation, and that helped to propagate the MJO off to the east. We also saw that long wave anomalies and latent heat flux and short wave anomalies, latent heat flux anomalies were in phase with precipitation and water vapor, so that helped to maintain the MJO. So primitive compared to what some of the subsequent analyses have shown, but this was the first paper that actually looked at the MJO in the context of the moist static energy budget. One thing I'll note here, this is also from a model. And so some of the partitioning between these two different terms might be different relative to the real world. So for example, long wave isn't as big here as we've subsequently found, and latent heat flux in this model is a bigger contributor to its maintenance, but I'll show you later some more modern results that show you the magnitude differences of these. All right, so after that modeling work, Kieran, Mai, and I looked at the moist static energy budget in reanalysis data, and I won't go through all those terms here, but we basically found a similar, broadly similar idea with some differences between ERA, forget ERA 40, I can't remember what version of ERA it was at the time, and NCEP. And then subsequent to that, and I won't go through all of the gory details of this, as Alice and Wing showed, it's become very popular to look at moist static energy variance budgets for looking at various types of convective organization in the tropics. This is one example where you can actually use the moist static energy budget to look at propagation of the MJO. If you look at the dot product of each of the moistening terms with the moist static energy tendency, or maintenance of the MJO, where you look at the product of each individual term and the moist static energy itself. And this is actually an analysis that was done by, and I think I'm going to present some of Yu Chen's work tomorrow in my 15-minute talk, where she was applying it to the NOAA Unified Forecasting System and looking at how well it looked at, it looks like observations. I won't talk about these terms here too much. Basically, if you look at moist static energy budgets, use these to define what the maintenance and propagation of the MJO look like, you get the following picture, and I'm just going to talk about it schematically, based on this diagram from Angel Adames. So let's talk about propagation first. So basically what happens is in many budgets off to the east of convection here, the dominant term in leading to moistening and therefore eastward propagation is actually horizontal advection. Interestingly, and this is maybe a deficiency of this diagram, the major horizontal advection moistening source are actually these meridional winds that are being generated by these Rossby gyre-like features. Remember, I talked before that there should be Rossby gyres of opposite sign off to the east of MJO precipitation in this diagram. Those Rossby gyres of opposite sign actually lead to an anomalous moistening of the equatorial region by basically causing shutoff of extratropical air moving into the equatorial region. So horizontal advection, particularly with gyres of the opposite sense in this region, tend to moisten. You cannot neglect vertical advection as a moistening process in this region either. If you have shallow clouds, cumulus congestus clouds, you have bottom-heavy heating structure in this region that, through weak temperature gradient balance in the lower troposphere produces ascent in the lower troposphere. That acts as a moistening process. Also in this region, if you have positive sea surface temperature anomalies, that drives surface convergence and causes upward motion and causes moistening. So vertical advection also contributes as well. But horizontal advection generally has been shown to be higher. And then on the west side, these Rossby gyres here entrain dry air into the troposphere and dry the atmosphere. The other thing that I mentioned before that some of the moisture models don't include is that the atmospheric vertical profile looks very stratiform right here. And so the heating anomaly structure associated with that is positive heating in the upper troposphere, lower and negative heating in the lower troposphere. And that those negative heating anomalies in the lower troposphere will drive descent and cause drying. So there's also a strong vertical advective component to the drying that occurs in that region too. All right, so as far as maintenance goes, I mentioned anomalous radiative heating and anomalous surface fluxes. So remember this balance here. So basically, if you have a radiative heating anomaly and you know what the basic state stratification is, you can diagnose a vertical velocity anomaly that's meant to balance that radiative heating. And if you have that vertical velocity anomaly associated with radiative processes, it can cause a vertical moisture advection. So in this region of deep convection associated with the MJO, long wave loss to space is reduced, and so that is associated with an anomalous, mainly long wave heating of the atmosphere. That anomalous long wave heating with the atmosphere is balanced by upward motion, and then that upward motion drives a vertical moisture convergence. So if you didn't have any radiative processes, which I'll show you what happens in a model, if you don't have intraseasonal radiative heating anomalies in a model, like I'll show you what happens in a second, then you're missing a source of support for the moisture anomaly associated with the MJO by radiative heating driving air upwards. Then the other thing that can support the MJO are enhanced surface fluxes. So there are westerly anomalies down here at the surface. The MJO tends to occur in regions of a westerly basic state, and so adding westerly anomalies to a westerly basic state enhances surface fluxes, and that could also add moisture to the column to help support MJO convection. All right, so you can look at budgets to sort of infer the importance of various mechanisms for maintenance and decay, but you could also do model sensitivity tests. Kieran Mai and I in 2011 used an aquaplanet model with a tropical warm pool, so it wasn't zonally symmetric. It had a tropical warm pool, sitting, over, generally where the warm pool exists in the real world. And this model produced a very, very good MJO. So this is unfiltered data, and you can clearly see eastward propagating variability at about 5 meters per second, with a time scale on the order of, 40 to 50 days, something like that. And there's been other, variations of, experiments like this, like Murat Krudinov has done, Nathan Arnold, people like that. And then we did an experiment where we suppressed intraseasonal latent heat flux, radiative fluxes. And we did a really blunt experiment here where we basically just set radiative fluxes to climatology. I mean, there's other ways you can do this as well that, people like, Trotta Kruger and Bjorn Stevens have done, but we just set radiative feedbacks to radiation to climatology. And you can see that when you do that, there's a substantial weakening of, MJO variability in this model. Tropics become a lot less organized. And then another paper that I worked on with Dargan Frierson and Adam Sobel is we did a similar experiment, except that we turned off surface flux feedbacks. And so this is a control, and in this case, I'm showing 850 millibar winds. So you could clearly see eastward propagation here. And in this case, we see that with turning off surface flux feedbacks, you pretty much completely kill the MJO in this model. There may be some model dependence to these results. The model I'm using here is a former version of the NCAR community atmosphere model, where the MJO seems far too sensitive to surface fluxes relative to radiation. So there'll be some model dependence to this, but I like these sorts of experiments because you kind of break the link between a particular process and the phenomenon you're looking at. All right, so some more recent work to give a bit more detail on how radiative feedbacks help to maintain the MJO was some work done by my former student, Wei-Ting Shao, who's now at MPI. He just started at MPI like a month ago. And what he did was he took NASA series radiation anomalies and composited both long wave anomalies and short wave anomalies relative to the center of the moving MJO convective envelope in the warm pool region. So colors on this plot here show that you have positive long wave heating anomalies in the region of MJO clouds. And I think you could barely see the cloud field here in gray, so that's where the cloud anomalies are. So basically there's anomalous long wave heating in the MJO region. And associated with that anomalous long wave heating, Wei-Ting put that long wave heating into a linear baroclinic model to look at the response. And the response here is shown in vectors. So you can see that long wave heating produces an ascent of air, and that ascent, you could calculate a moisture advection from if you wanted to. So basically, long wave anomalies, especially if you vertically integrate over the entire troposphere, are producing a moistening associated with MJO convection. It's interesting, though, if you look at the shortwave component of the radiation budget. In the shortwave, there's heating aloft, but cooling in the lower troposphere. If you just vertically integrated these shortwave anomalies like you would do in the standard version of the moist static energy budget, the shortwave anomalies would come out to be zero, basically. They kind of cancel upper and lower. But the implications for the moisture budget are actually different. Remember that the vertical profile of moisture has strongest gradients in the lower troposphere and relatively weak gradients in the upper troposphere. So if you drive an upward motion in the upper troposphere, there's not much moisture up there, so that has very little effect on the moisture budget. But this descent that you see here due to shortwave anomalies in the lower troposphere, because the moisture gradient is stronger there, drives a pretty strong drying. And so if you vertically integrated the moistening effects of this anomaly, it would actually turn out to be a negative feedback due to shortwave anomalies. And so that's one bit of insight that you could get from sort of applying weak temperature gradient to the moist static energy budget and looking at it in a moisture budget framework versus just using the standard version alone. And then one other interesting body of work that Wei-Ting has looked at is how the strength of the long wave radiative feedback varies spatially. So how we're defining the long wave radiative feedback here is as a percentage. And so if you look at the moistening effect of the radiative anomaly and divide it by precipitation, you get a percentage of long wave radiative moistening relative to precip. And you see here that this is about 10% or so, depending on where you look. But I wanted to point out two specific regions where the strength of the radiative feedback is particularly strong. So first thing I want to note is that this is averaged over the entire year. We haven't broken it out by season yet. First place I want to note here is the Northern Indian Ocean is one place where the radiative feedback is particularly strong, sort of bracketing the land area here. And then another region is this region just to the west and north of Australia. If you broke it down by season, what you would see is that boreal winter, this area shows up, and in boreal summer, this area shows up as having a really strong radiative feedback. So what we think is going on is that this feedback is strongest in these regions where you have monsoonal flow in summertime, and regions where you have strong monsoonal flow associated with the Indian summer monsoon or the Australian summer monsoon. You tend to have stronger vertical wind shear. And if you have stronger vertical wind shear, that helps to produce more organized convective systems. And then the other ingredient that is also important for creating organized convective systems is high sea surface temperature as well. And so Wei-Ting plotted the frequency of occurrence of sea surface temperatures greater than 30 C and the co-location with shear greater than 8 meters per second. And those two conditions tend to co-locate, one in this region north of Australia, and secondly here in the Indian Ocean and across basically right over Bangalore across India. So maybe not coincidentally, you get really strong MJO and BSISO variability in these two regions. And in particular down here, this tends to be the region where the MJO propagates through the maritime continent between Australia and Indonesia. And it's a region where these conditions exist. Wei Ting has a whole bunch of other plots looking at convective organization as they relate to SST and shear at different levels and tropospheric humidity that I won't show here, but I found this particularly interesting. All right, I think I have 5 minutes or something like that, more or less. So I'm not going to show too many equations here. I'm just gonna sort of conceptually show you how people have put together some of these findings into models of the MJO called moisture modes. So what a moisture mode model for the MJO looks like might be the following. So remember that there's this relationship between precipitation and water vapor, this exponential relationship that I showed before. So if you initialize a model with a humidity field, you can determine what the precipitation distribution looks like from that humidity field. So that's the first thing that you might do. If you know what the precipitation is, and you also know what the radiative feedback is associated with that precipitation region. So Adamus and Kim have actually done quite a bit of work to look at how strong radiative anomalies are relative to precipitation in the MJO. If you know what that is, you could come up with a parameter R here that essentially bumps up the amount of diabatic heating in precipitation regions to account for this radiative feedback. And if you, and the other interesting thing that they found is that this radiative feedback parameter is scale dependent. And so it tends to be largest at the largest spatial scales and smallest at the smallest spatial scales. So this parameter here is really important for getting a scale selection mechanism for the MJO in these models. All right, so basically, you know what precipitation is, you know what the radiative feedback is associated with that precipitating region. So you have a component of heating here. There's this background radiative cooling here that they put in the model, and then you could also put in a sense of surface sensible heat flux, which is relatively small. But if you know what these heating terms are, through weak temperature gradient balance, you could derive a vertical velocity in the model. If you assume a background static stability of the model. And these models often are very simple, just looking at a first baroclinic mode type heating profile. It would be really nice to have more complexity in the evolution of vertical structure in the model versus what many of these include, but many of these have very simple parameterization. So anyways, once you know what precipitation is and the associated radiative feedback, you could derive omega. If you know what omega is, you can generate a large scale flow field that maybe looks like Modon's or the Gilles model, if you know what that vertical velocity field is here, and maybe vertical velocity peaks here at this red dot. So precip, you could then get vertical velocity, and then you could use that vertical velocity to force a flow field. And then after you have that, you have horizontal winds, vertical winds. You could come up with a parameterization for latent heat flux, surface latent heat flux if you wanted to. And, after you have all of those things, you could iterate the moisture equation forward. And so you could get a new moisture field that results from that. And then after you have your new moisture field, then you could go back to diagnose precipitation and then do the same thing again. So conceptually, this is kind of what a moisture mode model does. If you look at Adamus and Kim, or my study with Adam Sobel, I mean, there's like 150 equations, so I won't go through all of those. But conceptually, this is kind of the basis. So from the Adamus and Kim model, you can look at the behavior of the MJO mode that's created in this model. And what's shown here is a dispersion, wave number frequency diagram with some dispersion curves on here. There's a periodicity on this side, going from 14 days to 100 days. A zonal wave number on this side. In colors is the background OLR spectrum, I think. And then model behavior. I'm not going to talk about all of these different curves here because I probably won't remember what they all are. But the amplitude is shown by these big triangles here. And one thing Adamus and Kim really like to highlight here is that with this model, particularly this scale-dependent radiative feedback parameter, which is biggest at the largest scales, you tend to get biggest amplitude with this moisture mode model occurring at realistic zonal wave numbers 1 through 3, 1 through 4 that the MJO exists at. So that seems to be a pretty big success. Then very briefly, I talked about this before, but basically the dominant process associated for propagating the MJO eastward in the model are these Rossby wave-like circulations that are produced. And so if heating is here, if you look at the vectors, you see that there is the cyclonic Rossby wave gyres off towards the west. And off to the east here, you have these anticyclonic Rossby wave gyres. And this off-equatorial flow here actually causes an anomalous moistening out to the east of the MJO, which tends to propagate it eastward. All right, and then there's been papers also applying this theory to the boreal summer ISO. And obviously during boreal summer, there is a very different basic state than exists during boreal winter. This is the moisture field that you could see here during May through October, compared to November through April. And one feature that you see here just, basically right over India is that there's a very strong zonal moisture gradient in the mean across the Indian subcontinent. And this paper, which I was a part of, but also this paper argues that, because you have this very strong east-west moisture gradient that helps to support northward propagation through horizontal advection. And so this paper here in 2022, they called it a unified moisture mode theory for the MJO and BSISO, and kind of brings those two phenomena together, with the basic state, depending on season, determining the exact characteristics. All right, so let me wrap up. So I presented a couple of examples of two disturbances that have been proposed to be moisture modes. They're regulated by weak temperature gradients and a strong coupling between convection and tropospheric humidity. I didn't talk about some other disturbances that have been proposed to be moisture modes. Easterly waves, tropical depression type disturbances, monsoon depressions. That's probably another lecture, but those have also been proposed to be moisture modes as well. The other thing I'll note is that moisture mode theory has also been successfully used to describe how the MJO and easterly waves change in a warmer climate. So that's also something possibly for another full lecture. Some of the, especially some of the models, seminal models for the MJO in the context of moisture mode theory do have their drawbacks. One is that they often neglect variations in cloud structure and vertical structure of the MJO over its life cycle. And so, for example, if you're developing a moisture budget for the MJO, and your cloud type goes from congestus to stratiform, you really need to account for that when thinking about the effect of the MJO on vertical advection. So that's one deficiency. This also has implications for radiative feedbacks, because radiative feedbacks are stronger in the stratiform part of MJO convection. And so, in fact, they actually might lag the precipitation anomaly a bit. And so that's also another deficiency. Many of these models ignore boundary layer processes and the role for SST variability and forcing convergence in the boundary layer. So that's something Adam Sobel and I kind of fudged in our 2021 paper. No, 2012 paper, accounting for that. Also, frictional boundary layer convergence. That's something we also had to account for, because you can't simulate this using weak temperature gradient theory. Synoptic eddies like monsoon depressions, easterly waves, these have also been found to be important for the MJO's moisture budget. And these are also not included in many simple models for the MJO. And then of course there's many other, there's other deficiencies as well. But I do find that moisture mode theory provides sort of the most minimal model that you can to get many of the major characteristics of the MJO and other tropical disturbances. And I think with that, I'll say thank you very much.
So, I mean, you previously showed that, in your 2009 paper that, and also some of the consequent paper where people have done the propagation and maintenance budget of, and where even though we see that horizontal advection has a lot to do with the propagation of MJO, but when you look into the maintenance, you would see that advection usually damps the maintenance. I mean, it's always out of phase with precipitation. So, and there are also, I think you also mentioned something about recharge discharge in your old paper, which that concept is not much used in the later part of MJO study. But what I want to ask basically is that people also have looked into the same precipitation advection relation into smaller time scale. Like some of Adams's recent paper, they try to say that even LPS kind of structure is very similar to moisture mode, at least. But again, the advection precipitation relation, what I find is a bit weak. And when you showed that map of moisture, and you also pointed out that the gradients are very strong in the western part, and the eastern part is very weak. So do you think advection precipitation relation being weak for, and also we know that LPSs are mostly Bay of Bengal to eastern part of the Indian region specific case, because the LPS tracks are mostly more concentrated over that region. So do you think it's just a gradient issue, or maybe advection and precipitation relation is weak for smaller time scales because advection has an inherently longer time, let's say like 20 days, 15-day recharge, and then you have the discharge? Or is the time scale issue or just a gradient issue that we have a lot of moisture in the east, that's why you see a weaker coupling?
Yeah, I mean, so the BSISO unified theory argues that it's the large-scale MJO circulation which is advecting moisture across that gradient, and that's how you get northward propagation. It's not incredibly clean, though. This is the horizontal advection plot, which I didn't show. And this makes me nervous a little bit in that it's really patchy, really isolated. And also there is northward propagation here over the Western Pacific, which I don't have on here, with no gradient. So yeah, I am a little bit nervous, I guess, about this argument, more so than I am for the actual MJO itself. And then, when you go to eddies and the importance of advection for, monsoon depressions, I think the importance of that also has a very strong dependence on the life cycle of the tropical disturbance. So for example, Diaz and Boo showed that horizontal moisture gradients were really important at the initiation of the monsoon depressions, but after they matured a bit, it became much less important. So I think there's complications there as well. So I don't know if that answered your question, but I agree it's a very complicated.
So it can either be once the LPS kind of sets up, the gradient itself becomes very weak, the moisture gradients, or it can also be that, the inherent time scale of advection is a bit longer and the LPS doesn't really fit in because average time scale of LPS would be 6 to 7 days or something. But when you do a advection precipitation thing, it's a bit longer. So yeah.
The argument makes sense.
Okay. So yeah, so can we when we infer the MJO intensity from an RMM based index? What component of that intensity might be attributed to this long wave feedback?
I would actually be relatively careful about using RMM in order to diagnose MJO intensity of the precipitation area itself. That index is highly dominated by the large scale wind field. And the biggest variance in that index occurs actually in the westerly duct region of the eastern tropical Pacific, where you get strong eddy mean flow interactions and hemispheric transports and things like that. If I were to look at the amplitude of the MJO relative to the long wave feedback, I'd probably use something more like the OMI index, which is more convection based. So that's what I would do, I guess, rather than using RMM.
Okay, thank you.
Hi, thanks for the nice talk. So you talked about the propagation and the importance of horizontal advection of the moisture. So when we look into the moisture profiles background, we can see that there is also a zonal moisture gradient, especially of the Indian Ocean, which is decreasing as we move towards the Western Pacific. So in terms of the zonal versus meridional, if you think of the Rossby response and the easterly and the anticyclonic gyres, so how do you see that? What is the contribution, let's say regionally, if you see over the Indian Ocean versus the Western Pacific?
Yeah, zonal advection is also very important. It's meridional advection I see being a bit stronger, but back when I did my first analysis in the GCM, for example, I partitioned the flow into horizontal and meridional, and also looked at the vertical dependence of the advection. And in that paper, they were pretty much 1-to-1. But that's a model, and there are a lot of unrealistic characteristics of the MJO. But even in I don't think I have this partitioning, but Kieran Mai and I looked at that too in reanalysis. I don't think that this shows it, but we actually did partition this UDEL M term into zonal and meridional, and yeah, definitely the zonal cannot be neglected.
Thanks. Also, one more thing. So this whole idea of this moisture being the important factor for the MJO propagation. So there's also this idea that MJO consists of this multi-scale structures with westward propagating synoptic scale systems, which is coming up, especially the recent studies which suggest that upper level dry signals can induce lower level MRG sort of signals. And this system, westward propagating systems are embedded within these large scale eastward propagating systems. How do you see
Yeah, I think that is one of the deficiencies of the very simple models that we talked about here, because that multi-scale structure can help to lead to organization and radiate to feedbacks. That multi-scale structure can actually also have a strong effect on the surface Bondrelier momentum budget that affects things like surface fluxes. And so I think that where these models need to go next, Boulam's talk nicely talked about some of those aspects, need to include some of these multi-scale interactions.